Yeah, it's a pleasure to talk to you about what we've been doing a bit in the context of project PO3. So the overview of the talk is here. So first of all, I'll explain a little bit what is the state of the art of machine learned force fields within VASP. And yeah, really what we do routinely in VASP now. Then we'll talk about the application to thermodynamic properties in Zirconia. And then I'll talk about a specific goal of our sub-project, which is a delta machine learning for beyond DFT accuracy. And you already heard a great introduction, actually, to this in the talk of Anatol von Lilienfeld. And finally, a bit of summary and ongoing work. Of course, I would like to acknowledge immediately the people who worked. I mean, of course, Georg, this is a brand new picture on the TACO website. Peitao is a postdoc in TACO. Ferenc Karsai is an employee in VASP, and he's the main developer of the machine learning part in VASP. And Joske Ginucci, he's actually working for the R&D labs of Toyota, and he is the one who actually first implemented the machine learning potentials in VASP, so it wouldn't really be there without him. So the introduction to the work is really quite broad, very general. So it's kind of like the dream of many material scientists and physicists to be able to predict, free energies and phase transitions and thermal conductivity and all these properties with high accuracy. But all these properties require simulations that are very long in time and time scales, and also it requires us to be able to describe an harmonicity with really high accuracy. And what we have are, of course, first principles methods, which are, as you know, accurate but too slow. Of course, you could also argue whether they are accurate, but I'm putting in this box all sorts of methods, from DFT to more accurate ones. And then on the other side, we have force fields, which are extremely fast but inaccurate, plus suffer from transferability problem and so on. And then in the middle, as you all know by now, we have machine learned potentials. So machine learned potentials are really one of the common threads of the theory projects of TACO, and they offer the required speed and accuracy. So as you can see here, this plot shows a benchmark of the computational cost per MD step and per atom of different machine learned potentials versus also the errors. So of course there is a trade-off when you train a force field and you use one. There is a trade-off between the accuracy and the computational cost, and also it will depend on the specific potential that you use, the descriptors and so on. But you see, we are orders of magnitude faster than first principles methods, although of course still slower than empirical force field. There is also a lot of work in this direction in the literature to try and make machine learned force fields much faster. And here, since everyone likes surfaces here, this is an example of it's the Silicon 111 surface reconstructions, the 7x7 surface reconstruction. And DFT is able to predict that the 7x7 reconstruction is the most stable one, and so does the SOAP gap, which is a machine learned force field, whereas empirical force fields fail at predicting the stability of this surface, but they predict the unreconstructed surface is the most stable one. So this is to convince also you experimentalists that it should work. So I'm not here to tell you the story of machine force fields, but of course most people will tell you that the mainstream work started from here, from the neural network potentials of Baylor and Parinello, and from the Gaussian approximation potentials in Cambridge. And then many more works followed, and various ideas for how to write the descriptors and the models and so on. But the idea behind is really quite general and pretty simple schematically. So I borrowed this figure from a review paper. Essentially there are 3 steps. The first one is the construction of a reference database that we use for training, the representation of the atomic environment, so finding the right descriptors, and then we have the regression steps. So it can be ridge regression, neural networks, and so on. So I'll tell you what we do in VASP for the first step. It's what we call learning on the fly. So it's what we think is the most general and robust method for learning at the moment. Of course, it's not a golden bullet, but it really does work quite robustly. So what we do is we start off in VASP, reading in a force field if available. Otherwise, we start off doing an ab initio calculation. We make a prediction for the potential energy surface, but we also predict the uncertainty of this. And if the uncertainty is above a certain threshold, then we will do a first principles calculation, followed by our data selection process and the retraining of the force field, and then we keep doing our molecular dynamic steps. So now this is, we think, really, really efficient. So it allows us to train a kind of like a minimalistic set of training data. And of course, this requires having a good error estimator, and the framework of Bayesian inference gives us the tool, the Bayesian error. And as I said, this is fully integrated in VASP. Then just one brief slide to tell you what we do about the descriptors and the regression. So the descriptors are based on mapping the local environment around each atom onto 2 and 3 body atomic distribution function. I'll spare you going through these equations, but essentially it's very similar to the SOAP descriptors, with the difference that we use purely 2-body and 3-body descriptors, and then once we have, these are essentially the 2 and 3 body atomic distribution functions, and if you expand them using gradient and angular basis functions, you come up with a bunch of coefficients, which are our actual descriptors. Then the common step is that the potential energy of the system is written as a summation over all the atoms of the system, the potential energy associated to each atom. And this is a nonlinear functional of these descriptors. And then using the standard kernel trick, you write this as a linear combination of kernel functions. This is, for example, a polynomial kernel, and these x here are combinations of our 2 and 3 body descriptors. Now, afterwards, what you do is you put together all your ab initio data, this y here. This consists of energies, forces, and stresses for all the configurations in your training set. This phi matrix is the design matrix that include the kernel and the derivatives in order to describe forces and stresses. And these are the regression coefficients. And so all you need to do is to solve a least squares problem. Standard way to do is Bayesian linear regression. So essentially, you solve the what is called also ridge regression. So there is a regularization parameter that again has a probabilistic meaning. Or you can actually also simply calculate the pseudo inverse of your design matrix using singular value decomposition. So you can actually test not to use any regularization at all and see if you incur into problems of overfitting and so on. Now, the application, as I promised, is zirconia. Now, I do know that zirconia is more of a material that was studied in the FOXY project, but the truth is that we started working on zirconia before TACO, and the reasons for that are that it's really what we wanted. It's a strongly anharmonic solid. It has a low thermal conductivity. It's got very interesting phase diagram. It's got a monoclinic structure at low temperature, then becomes tetragonal, and then cubic at very high temperature. And of course, it's very important for many technological applications like solid oxide fuel cells and so on. So we set up to study this material, and what we did was our on-the-fly training, which made us gather just a few hundred, less than 600 DFT calculations. Of course, the quality of this DFT calculation is very important in order to train a high-quality force field. And we went to temperatures that are very high, up to near the melting point. And these are the errors, right? So these are the errors in energy, forces, and stresses. And the errors in energy, you see they increase in this region. This is because this energy region corresponds to the high temperature cubic phase. These are the actual values of the errors. This is just to show you that including regularization or not, does not have a major difference. Actually, we are more accurate when we do not include regularization with SVD. And also, these are the training errors, and these are the test errors in parentheses. So this tells you that we are not overfitting. This is the phonon band structure in the cubic phase. I wanted to show you this one in particular because you see it's got these negative or, well, imaginary phonon modes here that tell us that this structure is unstable, of course, as we know, at 0 temperature. But also, it's very, very important that our force field can quantitatively describe these imaginary phonon modes, because otherwise we cannot hope to actually then be quantitatively describing the phase transitions. Now, looking then at the phase transitions, what we can do, the simplest thing we can do is to simply do a molecular dynamic simulation in the NPT ensemble, so fixed pressure, and let our system slowly cool or heat up. And so you see what happens is this. When you cool the system, it stays in the tetragonal phase, whereas when you heat it up, you start to monoclinic, then there is this jump in the volume, and then tetragonal, and then in the cubic phase there is just a little bit of a change in the slope. So this is, typical first order Martensitic phase transition. And if we look at the actual values of the lattice parameters versus temperature, this is what we get. Again, compared with the experiment, it's pretty good. We're doing DFT with PB sol, which is pretty accurate, and this is the monoclinic angle. But of course, you cannot extract the transition temperature this way for a first order transition, because you will need to run your simulations forever and in a huge cell. So we needed to do actual free energy calculations. And so we did that using thermodynamic integration. So you do thermodynamic integration from a certain low temperature value, starting from a known value of the free energy, known by using the quasi-harmonic approximation. So the quasi-harmonic approximation only describes an harmonicity at the level of the volume dependence of the phonons. And so, of course, you can't expect it to be very accurate high temperature. And in fact, when you do quasi-harmonic calculations, this is the difference in the free energy between the tetragonal and the monoclinic phase. You see, it underestimates the experimental value where the monoclinic structure becomes tetragonal. And then when we correct this estimation, well, actually, when we calculate the fully anharmonic Gibbs free energy, we get an estimate that is, better agreement with the experiment, at least at this level of DFT description. And then for the tetragonal to cubic transition, now that's easier because this is more of a second order transition. You can just look at the tetragonal parameter and fit it, and again, you get a result in good agreement with the experiment. Again, remember that this has really, really high temperatures, and it's actually even hard to study experimentally. And this is a success of machine learned force fields because there are no empirical force fields that can do as well for all the different structures, all the different phases. And then we moved on to study the lattice thermal conductivity. Now, just a very short introduction on this. When, as a theorist, you set up to study the lattice thermal conductivity, well, the common way to do it is using a reciprocal space representation. So you look at the phonon-phonon scattering, and you solve the Boltzmann transport equation. Now, the Boltzmann transport equation only works at relatively low temperatures and not so strong an harmonicity. So then you can use other methods. You can use a real space theory where you look at the atoms moving in molecular dynamics, and there is a Green-Kubo theory, which is an equilibrium molecular. It's based on equilibrium molecular dynamics, and can really describe the full anharmonicity of the system, and it works for all sorts of crystalline and amorphous solids or liquids and so on. Now, the problem is that until very, very recently, people were even thinking that doing ab initio calculations of thermal conductivity with Green-Kubo theory was impossible due to some ill definition of the heat flux. Turns out that that's not true, but still it's really, really demanding or even impossible. And up to now, there's less than a handful calculations of ab initio Green-Kubo thermal conductivities. Now, the thing is that to calculate thermal conductivity with Green-Kubo theory, you need to calculate the autocorrelation function of the heat flux. And the heat flux is expressed really easily when you have many-body potential. Also taking into account periodic boundary conditions, you get this expression here. And this has actually been used quite a lot in the context of classical force fields. But again, classical force fields are actually not quantitatively accurate, and there's many results in the literature where you can see that that's the case. But this expression here can be used really straightforwardly, or kind of straightforwardly, with machine-learned force fields. So still, it is not straightforward because you do need to calculate many trajectories for quite a long time in order to converge these values. So you see here as an example, this is the heat flux autocorrelation function. You see that actually it goes to 0 very fast. So you see this scale here is a picoseconds, so just a few picoseconds, but still you need really long trajectories to get this. And this is an example then of the integration that gives you the thermal conductivity. And these are the results. So the red points here are our data, and these black ones are the experiments. You see the temperature dependence is really in good agreement. Also quantitatively, we underestimate a little bit the experiment, but there's various reasons for this. The agreement is really satisfactory, and you can see here these orange points are empirical force fields. They do not follow the right temperature dependence. There's also discontinuity when you have the monoclinic to tetragonal transition. So this is it for thermodynamic properties, and now I wanted to move on to the second part of the talk, which is delta machine learning beyond DFT. And again, as I said, this was also a specific goal of our TACO project. So as we talked about also in the talk of Andreas Grunheis, you heard it a lot, that as you know, DFT works very well, but it's not very accurate for many problems. And when you train a force field, when you machine learn a force field, that's going to be only as good as the underlying theory that you train it on. So we wanted force fields with beyond DFT accuracy, and in order to train on, let's say, RPA calculations, you will need it will quickly become really unfeasible if you have to do RPA calculations for similar sort of supercell sizes and number of training structures as we do for normal force fields. So the idea is that we only need to machine learn the difference between this higher level calculation and the underlying DFT calculation. And this is not a new idea. You heard it also in the talk of Anatol von Lilienfeld. It actually came from him originally, and then it was used also later on in other publications. Now, what we focus on here is solid-state systems. Well, that's what we want to do. And we focus on really having a solid strategy for this delta learning and of training a force field that can predict not only energies but also forces and stress tensors. So where we can use for molecular dynamics and all sorts of applications. So really, we wanted to go full in with this delta learning, and we focused on the random phase approximation. So it's been shown many times in the literature, also in many of Georg's publications, that RPA works really well. Also describes van der Waals interactions. And the advantages of doing RPA in VASP is that there are very advantageous cubic system size scaling algorithms. And also recent development is that you can also calculate forces at the RPA level in VASP, whereas for the stress tensors, we still use finite differences, but that is not so expensive. So the general scheme is this. It does look a little bit complicated, but it's not. So it's very simple. You start with the standard on-the-fly learning, from which you extract your data set that gives you your, let's say, low-level force field. And then you do another on-the-fly learning from which you extract another data set. But this on-the-fly learning, you will do it using smaller supercells. So supercells that you can afford to study using, for example, RPA. And then you use, for example, the COR algorithm to do a rank compression of the kernel matrix that essentially throws away a lot of these structures when you use, let's say, descriptors with less resolution. And so this gives you your new data set that is much smaller than the initial one. So again, it contains smaller supercells and fewer data, let's say of the order of 100 structures. And you use this to machine learn the difference, and then, of course, you use this MLFF delta to correct your initial data set, and then you can finally train a force field that ideally has the same accuracy as training directly on, let's say, RPA. Of course, we need to check if this worked. So in the test case, which is again Zirconia, because we already knew it very well, we used as low-level method PBE, which is even less accurate than PBE stall. And as high-level method, we used the DFT scan as a kind of toy test and RPA. So again, in the initial training data set, we had this less than 600 structures. And then for the RPA delta training, we had 168 structures. Actually, later on, we figured that we could even use fewer structures. So all this has been done by Pei-Tao Liu in our work. He figured out and tested thoroughly all this strategy. And so Pei-Tao then went on testing. And what we have here is the tests using scan. So this is just PBE. This is a training directly on scan, and this is a training with the delta learning strategy. And you see that the errors between scan and scan delta are very, very similar. And then these are tests for RPA, where we calculate, again, test errors comparing PBE and RPA delta. Now, these errors for energies and stresses are a little bit higher than what we see here, and this is because we're using smaller supercells. There's very simple reasons why the errors are larger. But anyway, the important thing here is that you see the errors between RPA and PBE are very similar. Again, telling us that the method seems to be working. Of course, we need some more testing. This is testing on the phonon dispersions. So again, taking all three phases of Zirconia, we look at the phonon dispersions, and within VASP, you can actually, because you can calculate forces, you can also calculate phonons. And Pei-Tao did it for the gamma point. And so you see the red curve are the phonon dispersions calculated with the RPA delta force field. And they agree pretty well with the direct RPA calculations, which are the blue dots. Finally, we redid all the calculations that I showed you before, this time at the level of scan and RPA. So again, the simple heating and cooling of the system, and then the thermodynamic integration to get free energies, and also look at the tetragonality parameter to extract the cubic to tetragonal transition temperature. These are the results. So you see that PB sol is already quite great compared to experiment. Scan is an improvement, and RPA again confirms that it confirms the expectations that it's even more accurate. So this is the proof of concept, but also a nice result. So this is the summary of what I told you so far. Georg is there, so I'll skip through this. But I wanted to acknowledge again everyone who contributed to the work. And then I wanted to very, very briefly say something about what has been going on top of this. And we had a PhD student, Bernard Schmidtmeyer, starting in summer. And his main goal at the moment is the learning of tensorial quantities, which is, again, one of the goals of our TACO project. What we do then, once we learn, for example, Born-effective charges in ionic materials, is that you can calculate infrared spectra from essentially, you need to get the Fourier transform of the autocorrelation of the polarizability derivative, which is polarization, sorry, which is proportional to Born-effective charges. What Bernard has been doing together with Caroline Faller, a master student, is a new force field implementation, is a separate Python package. And on top of this, we want to implement the lambda slope method, or symmetry adapted Gaussian process regression, as it's also known. Essentially what happens is that when you have a tensorial quantity, that transforms covariantly under rotations of the systems and so on. And what you want to do is to incorporate this covariance in the training and in the predictions. And you can do that with this method, where essentially you can generalize the descriptors using Clebsch-Gordon coefficient. And so then your kernel will also be generalized and will become a 2 lambda plus 1 times 2 lambda plus 1 object, where lambda is the reducible spherical component of your tensor. We will pair the lambda slope method with derivative learning, essentially exploiting the fact that the Born-affected charges are derivatives of the polarization of the system. And so we set up the polarizations to be functions of the local environments, and then we directly learn the derivatives, which are the Born-affected charges. And hopefully next time we'll show you results on this. So this is really the end, and thank you for listening.
Thanks, Carla, for this very nice presentation. Questions? Christoph.
Thank you. Very nice talk. So I have a question concerning the delta learning. Wouldn't it be better to learn the difference between the high-level quantum data and the machine-learned potential that you obtained from the low-level description?
Yes,
because that's what you're eventually going to use, right, in your simulation?
You could do that, but we actually did test that as well. I mean, the results in practice are very similar.
Any other questions or comments? Michi.
In this delta learning, can it happen that you have discontinuous changes of the electronic structure? I mean, if you calculate something that happens at 2000 Kelvin, probably it's not relevant. But if you go to lower temperatures and the electronic structure changes discontinuously, then probably you have not much chance with this, or the concept of this.
You mean if the discontinuous, so when you compare the, let's say, your DFT and your RPA?
Yeah, or say if you have some whatever metal insulator transition or some discontinuous thing, the electron hopping from one place to a far away other place or something like this.
That would definitely be problems then, yes.
So there are no clean concept so far, or
that is a big can of worms, probably.
Questions or comments? So let's thank Carla again for her talk. And